Can you hear me? Yes. Wonderful. So thank you all for coming tonight. Thanksgiving celebration and all. So as Rachel said, my name is Shardha. I'm department chair, but I've also been a professor here for 13 years at UT. And my research is on galaxy evolution. So you know how galaxies form, how they grow into these amazing systems like our own galaxy, the Milky Way. So I hope to share some of that with you today, as well as focusing particularly on galaxy mergers. And when I say galaxy mergers, I mean, you know, the collision of two galaxies, they merge into one single system. And these galaxy mergers really, they play an amazing role in shaping the universe around us. And I will share some of the exciting things they do with you today. So the first thing that galaxy mergers do for us is mass buildup. So if you look about 13 billion years ago, when the universe was about 5% of its age, you see many galaxies. You know, they were low mass, they were irregular, they don't even look like galaxies. And if you look today, you see massive galaxies that are maybe 100,000 times bigger, including our own Milky Way, which is a spiral galaxy. And so one of the ways you can do this mass buildup and grow galaxies is through these mergers. So that's one way, mass buildup. But mergers are actually quite exciting. They don't just, you know, boringly just build galaxy mass. They actually can do dramatic transformation to the shape and the structure and the kinematics of these galaxies. So I'm going to illustrate that with this movie, this simulation. And what I want you to bear in mind is, again, if you look today in our universe and you look at massive galaxies, there are two kinds of galaxies. There are spiral galaxies like our Milky Way. They are pancake-shaped. Just think of a pancake, it's flat. And then we have huge, massive system called elliptical galaxies, and think of them as watermelon-shaped. Okay, and one of the dramatic things that a merger can do is you can crush two pancakes together, so two Milky Way-type galaxies, and you are going to build a watermelon-shaped elliptical galaxies through that process. And this process happens, I want to tell you a little bit about the physics. So it happens through three things that I want you to look at while the simulation is happening. There's going to be gravity, shocks, and something called violent relaxation. So I'm going to show you the movie first, and then we'll talk about it. Okay. So gravity, as you can see, is pulling two of these spiral galaxies together. The yellow stuff is stars, and the blue stuff is gas. Okay, and of course, these things are not rotating. It's just a perspective, right? And so you can see gravity has pulled them together. Then there's something called gravity torque, which is related to the force of gravity. It's like a leverage on it. And the gravitational torque, you will see, is driving all the gas, the blue stuff, towards the center of the galaxy. Okay, so gravity and shocks are driving the gas to the center. And now there's something strange that's happening. Notice as the movie is moving around, you can see the shape is becoming more rounded. And that is happening through this funny thing called violent relaxation. So I'm going to show you the movie again and talk about violent relaxation. So what violent relaxation is gravity is changing very quickly. So the particles get all confused. You know, they're basically being kicked in 10,000 directions at the same time, and they forget that they were moving in this pancake shape. And they start to move in all directions equally. And when that happens, you can visually see it. You will take a disk, a pancake, and basically puff it up in all directions. And you can see that happening right there. That was violent relaxation. The other thing I want you to see, of course, this movie doesn't go all the way, so you don't see the full transformation. But, you know, this is not some crazy imagination of astronomers that running this simulation. You can actually see it has some bearings to reality. So on the right-hand side for you, there is this panel of galaxies. These are actually real images of galaxies that we have observed. And what you can see is that during the simulation, let's try it one more time. You can see that as the simulation is going on, you can see phases in the simulation that you can match to actual observed system. So the very top there were two galaxies starting to come together, and the middle and lower panel you can see the systems are starting to violently relax here, and you can start to see those systems actually in the real universe. Okay, so that's one thing galaxy mergers do for us. They also radically transform the structure. And here I'm actually showing one of the systems that we have observed called the Antennae. People used to say there's only one major merger happening in the universe because everybody just shows this picture. And you can see why. It's a spectacular image, and it shows two galaxies, colliding. The stuff in the middle is gas that is stripped between the galaxies, and it really matches some of what you see in the simulation, but this is spectacular, and you can see the young stars forming, the gas being compressed, and all the mess that's happening during the mergers. This is one of my favorite montage. What it shows you is actually, it's again a reality check, because in simulations, we have to model incredibly complex physics, right? We have to model gravity, we have to model gas physics, we have to model hydrodynamics. And it's very useful to do a reality check and see, as we do this simulation, do they match real galaxies in the universe? So this is a montage that was created by Frank Summers at the Space Telescope Science Institute, which manages NASA's mission, including the Hubble. So you're going to see simulation, and then you're going to see how it matches real galaxies. So that's simulation. Two things are colliding, and that's it's matched to an actual observation. The simulation is continuing, the galaxy mergers is continuing, and now that's an actual system. Okay? Simulation is continuing, and there's an actual system we have observed. Okay? So at least qualitatively, we must be doing something right, even if we don't get all of the details. So the third thing I want to talk to you about that mergers do is, mergers actually are the ways we build most of the stars in the universe. So mergers drive a lot of the gas you saw in the simulation towards the center of a galaxy. And then you have huge bursts of star formation. We call them starburst. And they produce perhaps 90% of the light from the galaxy is actually coming from the center as a result of a merger driving gas. And then you might also know that galaxy centers have black holes. So what these mergers do is they also drive tons of gas in the center, drain them of angular momentum, and it feeds the black hole. So it's one of the ways we grow black holes in the universe. So this is a simulation where, I'm not sure if that one is working. Okay, so let's try that one again.
Just let it run, sure. It'll crack, so just let it run.
Use your imagination, okay? Okay, so now what you can see in this simulation, we are not focusing on the stars, we are really focusing on the gas. So you can see two of the galaxies coming together, and the gas is being driven towards the center. The colors tell you how dense the gas is becoming. And so you can see it in the images. There's so much gas in the center. We don't show you the stars, but a lot of that gas is actually building new stars. The black hole in the galaxies are also in the center, so they are also growing. And now this system is starting to coalesce into one single system. And if we want to get picky about the detail, there's a lot of gas that's blown out. This is called feedback at the end. We don't actually model that correctly. So there's too much gas that's blown out in this galaxy. Mergers are not that violent. They are somewhat violent, but not as violent as in this simulation. But again, this shows how you can build stars and build black holes through mergers. Okay, so I hope I've convinced you mergers are incredibly powerful things. But their exact role in shaping the universe is something that astronomers are still trying to figure out. There are a lot of hot burning questions where we want to know what mergers do. And so I'm going to show you a few of them, open questions still. So yes, you've seen how mergers build galaxies, transform their structure, but statistically speaking, what is their role in actually building galaxies? So I'm going to show you this simulation here, which shows that actually galaxy growth is not just mergers. It's not just two big things colliding, which we call major mergers. It's also, you will see big things colliding with small things, that's called minor mergers. You will also see something called gas accretion, where cosmological filaments are bringing gas and growing galaxies. So that's another pathway for galaxies to grow. And astronomers are still trying to understand at different epochs what is the importance of these different processes. Okay, so we are starting 12 billion years back. The universe is 5% of its age. There's an overdensity somewhere in the universe, and you can see the overdensity attracts others. You are starting to build mass. You can obviously see some of these structures are merging, so you have major mergers at work. But notice also there's a lot of filamentary structure where gas is just flowing in and actually building the galaxies. This galaxy is starting to look pretty close to the Milky Way. It has what we call a bar, it has a disk, it has structure, and it is having little things collide with it. We call that minor mergers. I didn't talk about those, but those are also very important, very frequent. And so in this case, in 12 billion years, we are able, through this process, which takes into account all these growth modes, to build something like the Milky Way. And again, qualitatively, we get it right, but we're still trying to understand what is important at different epochs. The other big thing that we want to know is, well, if I look at stars in the universe today, how much of these stars at different epochs have been built through mergers? So this plot looks complicated. It's a plot astronomers love. We call it the Madao plot, after Piero Madao. And basically, the y-axis is showing you the amount of star formation in the universe. So how many new stars are you building? The x-axis is looking back in time. So 0 means today. 10 billion years back is about, the universe is 3.7 billion years then. And then 12 billion years back, you are looking at the universe 5% of its age. So you can clearly see something happened in the universe where the amount of star formation activity peaked 10 billion years ago. And then it's continuing to decline. And astronomers have been trying for a long time to figure out, why did the universe shut down, right? Why has it been stopped or producing stars less efficiently with time? So we've looked at this answer, at this question, and at least going back to about 6 billion years. So if you look at this plot on the top axis here, we've figured out the answer going back 6 billion years. And I will show you how we figured out the answers. So we'll use the Hubble Space Telescope about 6 years ago, and we looked back in time. And these systems that you are looking are actually galaxy mergers that have really been observed. This is not simulation. This is when the universe was half of its present age. These are the kind of mergers we see. It's very gas-rich. It's interesting things are happening. But the interesting thing is we don't see too many of them. And therefore, when we say how much of the total star formation rate over half of the age of the universe is coming from mergers, we actually find it's only 30%. Okay? So mergers can do great things, but they are not doing most of the star formation building over that epoch. Something else is doing that. So that was an interesting finding. Now we've only gone back 6 billion years. And we would like to go back further now and actually answer this question over the whole age of the universe. The other thing we are trying to figure out is, what is the role of mergers in different environments? So, for time immemorial, astronomers have been puzzling about an important question. If you look in a high-density environment in the universe, that's the picture on the left, you see completely different galaxies than you see in a low-density environment that you see to the right. So the high density is like the city center. The low density is like your rural region. And you can see galaxies like the Milky Way only exist in this low-density region. In a high-density region, we have mostly these elliptical galaxies. So it's been a puzzle as to why there's such a different galaxy population. And so we are looking at the reason and the role of mergers in potentially driving this process. And I'm very proud to say that we have a UT-led collaboration with UT and Texas A&M that is funded actually to look at this question. And there are 3 of the wonderful graduate students who are actually working. They do the work, actually. So lots of exciting things to come. And so you can see there's a lot of unanswered questions. We are going to be employed for quite a while. And I think the future is going to be bright, lots of excitement, and it's also very exciting that I think Texas astronomy will have a big role to play in advancing this breakthrough. So we are hiring the best minds in the field, but also we are giving them the best facilities they can use. So we have our own McDonnell Observatory in West Texas with the upgraded Hobby-Eberly telescope you can see, just upgraded last year. We have the best supercomputing facility with the Texas Advanced Computing Center. It does high-performance computing, machine learning. And then a lot of our faculty, and Steve is one of the leaders, he's going to talk next, of involving the James Webb, which is launching in 2019. We had a first round of proposal, and I'm proud to say out of the 106 proposals were submitted, 13 were accepted, and 5 of the 13 had faculty members and research staff from our department. So that's huge. And so, James Webb will be a successor to the Hubble. It will allow us to look back to maybe to 1% of the age of the universe. It's going to be launched at about 1 million miles above Earth. It's going to be very sensitive because it's way out there in space. The background is very low, and it has a big dish. But more excitement is coming with the Giant Magellan Telescope, it's the next generation telescope. It's going to be about 25.4 meters in size. So it will be one of the largest, or possibly the largest ground-based telescope on Earth. And the nice thing is UT is a 10% partner in that. So just to give you an idea, entire countries are joining to be 5% partner. And of course, in Texas, we think big. So we are a 10% partner. And that will be fantastic. And I will show you one slide to illustrate that. So there's going to be many breakthroughs with the GMT, about first stars, first galaxies, black holes, what kind of planets do we see outside the solar system, how many are habitable, dark energy, dark matter, and so on. But I want to talk about galaxy mergers and show you 2 amazing things. You've all seen the power of the Hubble Space Telescope, right? Fantastically sharp images. Well, GMT will be 10 times sharper than the Hubble. And I'm going to show you this image, which is a ground-based image, and what we could do if we were looking at this with the GMT. Okay? So that's pretty good. And for galaxy mergers, when you have these galaxies that are colliding, we are going to be able to, disentangle the 2 systems that are merging and do it at very, very early epochs. But it's not going to be just sharp. It has a huge field of view, which means we can look at many, many objects at the same time. And on the right here is actually a figure courtesy of Steve. The green is basically the field of view, so the area you can map from the Keck telescope, which is the largest ground-based telescope we have now. The blue one is the field of view for the James Webb telescope, which will be deeper, but it's a small field of view. The red one is the GMT. So not only will it be incredibly deep, but it will be able to observe maybe 50 galaxies at once while the other system observes 3. So we will be able to get tons of statistics and go deep, go early epoch. So that's going to be really exciting. 2023, a few more years. And I want to end on a more personal note. As someone who's in science, a woman in science, someone with a 9-year-old daughter who's in the audience. So I think the future is bright, but it would be even brighter if we could advance the representation of women and underrepresented group in STEM. And already we have national report that say the US, to be competitive, has to produce over 1 more million STEM graduates. And really to do that, we have to tap into the full diverse talent that we have in this country, including women, including underrepresented groups. And there's been a fantastic report by the AAUW, American Association of University Women, asking at why so few women. And they find women and girls are underrepresented starting from K5 all the way to PhD and above. And, how to advance women in this field is a long discussion that we can have offline. But I did want to pass on a few things as a parent to parents or family members who would like to encourage girls to be in STEM. So remember that social and environmental factors really shape the girls' achievement and interest in STEM. And that's one of the main findings of this report, and they go into great detail. And the thing I want to really push forward is the growth mindset. So believing in the potential for growth in and of itself improve the outcomes. And it's important to teach kids to grow these skills, that skills can be grown. And this is the whole premise of growth mindset, because they found that women and first-generation students and underrepresented group in STEM, when they face the first obstacle, the first setback, they tend to give it undue importance and to think it's a label on their skills. So teaching them that setbacks are just part of the journey, and that skills that you don't have can be grown, can be acquired. That's the basics of growth mindset, and it's incredibly powerful. And I'm very happy to talk to parents or kids with interest in STEM. And while I was pontificating about growth mindset, I went to my daughter's school one day, and the next slide is the contribution from her. So they have the best representation of growth mindset that I've seen. It's a poster that the kids and the students have set, and it's called the power of yet. So they are trained to say, I'm not good at this yet. I can't do this yet. I don't know the answer yet. So I thought that was a marvelous poster where they're actually doing this in school, and I'm just talking about it. So I thought I should put that up. And if you like the poster, my daughter Anne is there, so you can thank her about for the poster. Okay, so with that I will end, and I'm happy to take questions, and thank you for your attention.
All right. Thank you, Cosmic Fireworks. All right, we have time for questions. I'm going to scan the room before pointing at those. All right, let's start in the middle.
How long do these mergers take?
How long do these mergers stay? So the signature of the mergers, this distortion that you see, depends on what we call the dynamical time. So if you can think about the time it takes for things to mix together. So in the center of galaxies, the dynamical time is a few million years. The signatures get wiped out very quickly. In the outer part of the galaxy, where it's bigger, the dynamical time is several billion years. So you can actually see this signature for several billion years.
All right, next question. All right, up front.
Okay, in the case of two galaxies that are coming together to merge,
Yes.
assuming they both have one of those supergiant massive black holes in the middle, would those come together and merge first?
Yes. Yes, so they expected to coalesce around each other and merge. And in fact, in that simulation that I showed where I said, be careful about this excessive expulsion of gas. So basically when the black holes merge, there's a lot of gas that gets dumped on them. And on the accretion disk around the black hole, a lot of that radiation that's coming gets coupled with the gas, and that's what drives the gas out. And the reason we have too much expulsion is in order to correctly model that coupling between the gas and the energy, the kinetic energy and the thermal energy, you need to have very high resolution. So simulations don't do that part well, but that's kind of an addendum to your question. They do merge. The violent relaxation happens, actually I'm not repeating the question maybe. So the question was about mergers of the two black holes when the galaxies merge. And they do merge if they have both central massive black hole. And the follow-up question was whether that is responsible for violent relaxation. So for violent relaxation, it's not necessarily related to the black hole. Even if you don't have a black hole, you just have two galaxies merging, you will have it. And the way to think about it is imagine a particle in the center of the potential of that galaxy. When it's merging, basically the potential is changing so quickly that that poor particle in the middle, it just loses memory of what it was doing because it gets pulled one way, it gets pulled another way. And so violent relaxation is just related to the potential changing quickly, which means you need to have a lot of mass and it needs to change its distribution quickly.
All right, time for one more question. All right, in the middle. Thanks for all the help.
Will you make copies of that poster available?
I have it on my phone. I can send it.
Jumping the queue. All right, let's go back to the middle.
causes galaxies to start spinning?
That one, okay. So galaxy spin is a property that the galaxies do irrespective of mergers. We don't totally understand why that is the case, the spin direction and the spin orientation. It has to do with angular momentum of the gas that settles in and collapses, and you have to preserve the angular momentum. And if you have a couple of different systems, you have to preserve that angular momentum of the gas. And so that is basically this ordered rotation in a disk galaxies is tied to the angular momentum of the gas.
All right, let's thank Cosmic Fireworks one more time. Professor Shardha Jogee.